Okay, so here's kind of where we were last time. It's sort of a new topic, sort of the same topic. It's going to feel like a new topic for the first couple of minutes. Let me just remind you, we were talking about the fundamental theorem of line integrals previously. Okay. So path independence, at a first glance, does not appear to be the same topic. But let's make the definition. What it means for a vector field to be path independent is that the value of the line integral depends only on the endpoints of the domain of the curve. So it only depends on where you start and where you end. So the idea is that if you go along one curve, or alternatively, if you go along a different curve, now as long as you start and end at the same points, mind you, right? That the value of the line integral is the same. So whether you go along the one curve, whether you go along the other curve. So we say the vector field is path independent. Path independent vector field if this is the case. Now, I emphasize this has got to be true for all possible curves that start and end at the same 2 points, starting at A, ending at B. It's also got to be true for all A's and B's. Right? So it's a huge requirement. It's almost implausible seeming. I mean, after all, how could it be that a calculation I'm doing on that green curve will be the same as will get the same result as a calculation I do on the blue curve? They're totally different curves. Okay, they agree on 2 points. But other than that, they are totally different curves. And again, not just green and blue, but also every other possible curve between those 2 points. And furthermore, pick any other different 2 points. Any possible curve between those 2 points will always give you the same value of the line integral, independent of the curve and depending only on the endpoints. Seems highly infeasible. Okay. So one thing I want to emphasize before we go on is this is easily and often messed up, but this is a property of the vector field. So it's a mistake to say, it doesn't make any sense at all to say this curve is path independent. That's not a thing. Right? We're talking about the vector field. The vector field has this feature. It's also just a little grating to say the integral is path independent. Because, well, look, I mean, the integral, there's several things that go into defining what integral you're talking about. There's the vector field and there's the curve. And it is not that pairing that we're talking about. It's the field itself. The vector field is the thing that's path independent. Okay. All right. So, and now I'm going to make a shocking observation. Not only is this not infeasible, but there's lots and lots and lots of vector fields that have this feature of being path independent. In fact, all gradients are path independent. Real quick argument. I'm going to prove this with the fundamental theorem of line integrals. I do want to get a disclaimer out there quickly first, and that is just to remind you that in this discussion and everything we're going to do in this entire chapter 15, I'm going to shamelessly sweep under the rug issues of regularity. Is this continuous? Is this defined everywhere in the domain? We're almost never going to talk about those sorts of issues. It just makes things much more complicated, and it's a lot easier. First time through, I think there's plenty to still digest, plenty to talk about, while completely ignoring those issues. And I will say that things do get weird if you have regularity problems. It does not go through as you would expect. Okay, that said, now let's remind you of what the fundamental theorem of line integrals said. The fundamental theorem of line integrals says that if you have a curve, let's look at C1, and if you're looking at a line integral over C1, specifically looking at a line integral of a gradient. So let me rewrite not just some random vector field, but gradient of f, some anti-gradient function f. Then the value of that line integral is f of b minus f of a. Okay, so reminder, I'm trying to show that all gradient fields have this feature of being path independent. Okay, so that's on that curve. Now, but okay, let's also write down what does the fundamental theorem of line integrals say on this other curve over here. Oh, wrong. I did the wrong one. Sorry. C2. On that curve C2, the fundamental theorem of line integral says that if you're doing a line integral of a gradient, reminder, thinking about gradients, fundamental theorem of line integral says that you can compute that with, f of b minus f of a. Oh, whoops, wrong color. Fundamental theorem of line integrals on C1 says that. Fundamental theorem of line integrals on C2 says that. So, is it really that shocking then that these two integrals are equal? Is that really that weird? They're clearly both equal to f of b minus f of a. And furthermore, take any other curve. I don't care. Any other curve that starts at A, ends at B, well, you're going to get f of b minus f of a, and therefore it's not going to depend on the curve itself. Only on the endpoints A and B. Right? So it's one of these things. I like being real dramatic about this. When we first defined path independence, talk about what an outrageous suggestion it is that such a thing could even be possible, because it's easy to show that it's not only is it possible, but it's routine. All right, so let me take a pause before we go on. Does anybody have any questions about this neat fact that we've demonstrated here? Again, reminder is by looking at the fundamental theorem of line integrals, all gradient fields, if that is a gradient, then it is path independent. Okay. All right, cool. All right, so also true but harder to show is that, and again with regularity swept under the rug, not only does gradient imply path independent, but furthermore the other way, every path independent field is a gradient. So this is goes both ways. In other words, these are the same vector fields. Again, regularity ignored. Okay, so if you have a gradient, then it is simultaneously path independent. And don't forget, long ago we talked about how we knew that gradients are vector fields whose curl are equal to 0. I'm in 3 dimensions at this point, by the way. Okay, so this was the lifetime theorem thing that we talked about. Now, full disclosure, geometric intuition. Why is this true? We're going to have better tools to understand that geometrically and get a sense of it later on. So for the moment, I'm just asking you to take that on faith. Okay. All right. So I think this is interesting too. So what we have now is 3 different properties that all, as it turns out, describe the exact same vector fields. The vector fields that are gradients of something, right? That's a requirement to be satisfied. This is a gradient of something. Well, those are exactly the same fields as the fields whose, if you compute their curl, you get 0, and those are exactly the same fields that have this feature of being path independent. Namely, change the path all you want, just don't change the endpoints, and you won't change the value of the interval. Okay. All right, so that's it's a real eyebrow raiser that 3 different characterizations of the exact same vector fields. Okay, here's an example. Suppose you want to compute this line integral here. Our curve is top half of the unit circle oriented clockwise. So let's see here. Here's our curve. Right. We've got a vector field given. Our vector field is given by that formula. So we've got, some vector field, whatever. This is not intended to be realistic. But anyway, so we have a vector field, we have a curve, and want to compute the line integral. Okay. All right. So I'm going to show you how we can do this. A real neat argument. So first observation. Now this is, you'll notice, in 2 dimensions. And in 2 dimensions, it's not curl. It's Green's operator that allows us to decide with a lifetime theorem. Everything lives for 2 stages, right? If something's a gradient. So we're going to apply Green's operator. And notice Green's operator gives you 0. So this vector field is path independent. Right? So I'm going to take it the other direction here. Instead of observing that this is true and drawing a conclusion about that, I'm instead going to conclude that this is path independent. Let's use path independence to argue this. And here we go. If the vector field is path independent, then I can take this curve that I was given. Right? I'm asked to compute the line integral over this curve. And I'm just going to throw it away. Toss it. Right? I don't like that curve. It's all curvy and stuff. Right? I'm going to preserve the endpoints now. Now remember, that's one of our requirements. Talk about path independence. Path independence means you can change the curve all you want. You just can't change the endpoints. So we tie down the endpoints. I'm then going to pick a different path that starts and ends at that same point. And I like that one because it's straight and flat, and that's just easier. Right? Life is good. We got rid of all the trig that we would have otherwise had to deal with if we had been using that unit circle. So because the vector field is path independent, I can jettison that curve and instead use this curve. So here we go then. Here's the new integral that we're going to think about. Let me hit the pause button again. Anybody have any questions? Yes?
Can you explain the Green's operator again?
Yeah. So let's see, how many pages back? Oh, look, I had it right here, handy. Okay, so in 3 dimensions, here's our diagram that we talked about, and there's a bunch of stuff on here we haven't had time to talk about, but let's look at just this stuff here. So we drew this part of the diagram a long time ago, right? So the point is these operators kind of Lego together in a certain way. So gradients generate fields. Neato, curl, operates on fields, so I can compose those. And likewise, curls produce fields. Hey, cool, neato, that's what divergence operates on, the spit out functions, right? So we observe that you can compose these, and the mysterious fact that I asserted is that everything has a lifetime of 2, right? So in 3 dimensions, the way you can decide if something is a gradient, you have some vector field and you want to decide is it a gradient, compute curl, see if you get 0. Right? So that's in 3 dimensions. If you're in 2 dimensions, we have a different diagram to start off with. Right? And if you have a vector field and you would like to know, is that a gradient of something, you apply Green's operator to see if you get 0. So it's still that same, everything has a lifetime of 2, just in a different context, this being an R2, the operators that are there are just happen to be different. Yeah, it's a good question. Okay. Right. So, we have a new integral. Now, there's some nice features of this new integral that we're considering. For one thing, notice y is equal to 0. Well, that first component of the vector field was y, which I see evidently is always 0. So I get to rewrite my vector field. That's really nice. Right? If y is 0 for the entire calculation that you're concerned about, you can just plug that right on in there. No problem. Okay. And what that means then is that because y is equal to 0, it means that our vector field is pointing straight up, possibly down. No, up, because that's clearly positive, and therefore perpendicular to the x-axis. So that's just a neat observation that comes for free real quick. Secondly, though, notice that our differential dx is just your displacement differential along the curve. It's always parallel to the curve. The curve is parallel to the x-axis, so dx is parallel to the x-axis. So in looking at this dot product here, I'm looking at f dot dx. I'm looking at a dot product of 2 things that are clearly perpendicular to each other. And so that dot product is clearly 0, and I'm adding up a bunch of zeros, and therefore this integral is 0. Isn't that sort of suspiciously convenient? Right? Now, I'll confess I manufactured this example to be really convenient and nice, right? But you'd be surprised how often, again, 20% of the integrals that I did in my undergraduate physics major were 0 by symmetry, right? Ballpark. And so stuff like this, these geometric coincidences, geometric good fortune, happens a lot. And you should always be on the lookout for this kind of thing. But notice, in order to be able to do either of the sides of this argument, come here, eraser. In order to be able to do either of these arguments, I had to be on this curve, right? I had to be able to take my original curve that I was given. I had to be legally allowed to throw it away and replace it with this one, so that I could rewrite the vector field conveniently, and so that my differential would be purely horizontal. Right? So path independence is what gets most of the credit for this calculation. Path independence is what made it possible in the first place. Okay. All right. Now, so I think path independence is a lovely tool, but I now want to sort of confess something, disappointing about it. If you can conclude that your vector field is path independent, in other words, any path independence argument you can make, well, you could just as well observe that you have a gradient, and you could make a fundamental theorem of line integrals argument by finding the anti-gradients. So for example here, I could have just noted that this is clearly a gradient of something, right? And I just have to, think about, play the anti-gradient game and find what that anti-gradient is, and it's easy. F of B minus F of A. So there is something disappointing about path independence. It's a nice tool that addresses situations where we already had a nice tool, right? It's my favorite metaphor for this is it's a screwdriver, but we already owned a screwdriver, right? It's a second screwdriver. That's nice, but look, if you already have a screwdriver, having a second one, I guess you could screw two-handed then. But it's, how often is that going to be useful? It's a lot less useful given the presence of the fundamental theorem of line integrals. Okay. As a computational tool, but that point serves to segue into my next point, which is that not everything is about computing stuff, right? One of the big things that allows for other computational tools to be created is the idea that you can take concepts that are useful in one place and other concepts that are useful in a different place, and then draw connections between them, right? So one of the big things that math does is find connections between different ideas. And path independence does that also in a way that is extremely convenient. So real quick, I want to talk about physics a little bit. I'll be brief, but I want to talk about conservation of energy. So if y'all have had an introductory mechanics class, and I'm sure you've seen this idea of conservation of energy, not in the ecological sense, but in the sense that kinetic energy plus potential energy is a constant, and therefore we say energy is conserved. If, for example, if I were to drop my stylus, which I'm not going to do, these are expensive, I don't want to break it, but if I were to drop my stylus, by the time it gets to my hand down here, it would have a lot of kinetic energy. Well, that kinetic energy didn't just spontaneously generate, right? The idea is that up here, where it has no kinetic energy, it had something else called potential energy, right? And in this process of moving from up here, motionless but with a lot of potential energy, to down here, a lot of kinetic energy but less potential energy, this sum is conserved. Okay, all right. So wait a second. Can you do that? Is there such a thing as potential energy? How do I know I can define something called potential energy? And, well, here's my quibble. And I'm just, been trying to be worried about possibilities. But if there is a notion of potential energy, right, the amount that the potential energy changes as you move along a curve, that change in potential energy needs to be, well, how much work did you exert to move along that path? If there's going to be a meaningful notion of potential energy, the amount of work it takes for me to lift my stylus up to this higher point up here, that work has to be an amount of energy, which is the amount of energy that it preserves as it's coming down to down here. But wait a second. Between these 2 points, right, if I want the potential energy difference between these 2 points to be well defined, that difference also has to be equal to this amount of work. Right? The amount of work it takes to move along the blue path. Who says I have to lift my stylus straight up? What if, can you imagine, it's a little preposterous, but what if it were the case that by moving my stylus up to there in a helical path, all of a sudden it took less energy to do that? Well, then we would have a problem. If these two integrals here were different, then we would, what could this potential energy thing possibly be? I couldn't define potential energy if those two integrals were different. So, specifically then, it is the path independence. It is the fact that these two integrals are always equal. That makes it possible for me to define potential energy in the first place. Right? So, now did we just compute something? No, we didn't. Right? But a concept, potential energy, sorry, got ahead of myself. A concept, namely path independence, motivates the existence of a different concept, potential energy, which allows for yet a different concept, this idea of the conservation of energy. And this idea of conservation of energy, right, that this is constant, super useful computational tool. Right? So ideas that connect ideas to other ideas, seemingly, academics, abstract exercises lead to computational tools, right? So this is, I think, a wonderful argument for why path independence is important. Path independence allows us to talk about potential energy and the conservation of potential energy, conservation of total energy. Okay. All right. So, reminder, we have these three different formulations of a bunch of vector fields. They are gradients simultaneously if their curl is 0, simultaneously if they're path independent. Again, three different features satisfied by exactly the same vector fields. And now I just want to talk about lingo a little bit. It's not consistent. The preferred terminologies are not the same with all people that talk about the concepts. So, the way I would like to talk about these things is I would like to talk about this vector field as being a gradient. I think that's a very natural thing to call it. Look at it. That's what this equation says. F is a gradient of something. Right? It's right there in the equation. So I think it's extremely natural. That's not what physicists call this vector field. Physicists will call this vector field conservative. Fine. Okay, so the reason they will call this a conservative vector field is because, as we already know, these are vector fields that have that which is necessary to allow to define but a notion of potential energy that allows for talking about conservation of energy. So conservative because you can relate, with this vector field you can talk about a notion of conservation of energy. So, it makes sense from a physicsy point of view, but it leads to this, I think, slightly unfortunate reality that this vector field, you're going to hear two terms for this commonly, right? I like to call it a gradient. Again, it's right there in the equation. You'll also hear it described as conservative. So heads up, right? A lot of y'all are engineers. You're probably going to hear conservative. Okay. By the way, this thing here, as y'all know, I like to call it the anti-gradient because, again, it's right there in the equation. This is the thing whose gradient is the vector field you're talking about. Anti-gradient. What could be more natural? Right? Physicists will call this the potential function because this is the function that is the potential energy. If you go back and look through the potential energy argument that I made up here, that function is potential energy. So, okay, fine, right? But again, heads up, be aware you're going to hear both of these terms in different contexts to describe the little f. Okay. All right. So, one thing we're not armed yet to talk about is why this is a reasonable choice, but it is a reasonable choice. This vector field, same vector field, mind you, that I could call a gradient, or that others might call conservative. You can call it irrotational because we're going to see later on, curl in some sense measures a sort of a rotation, and I don't want to go into any more detail than that at the moment. We just don't have the tools to make sense out of it yet. But another common term is irrotational. And of course we also have, for that same vector field, we have this term path independent. So this is a little bit annoying, but altogether then we have 4 separate words to describe the exact same vector fields. Again, regularity swept aside, and all exceptions granted, when they're not regular. But for the simple cases we're considering here, 4 separate words, all referring to the same thing. It's a heads up. Right? Be on the lookout. It's going to happen in your future that at some point someone's going to say you have an irrotational vector field, and you need to instantly snap to and realize, oh, they mean it's a gradient, aka that it's conservative, and by the way, it's also path independent. Right? So you need to be on the ball with those associations. And apologies for the terminological clunkiness of how this works. Okay. All right. So moving along, we're going to talk about a new theorem today. This is called Green's theorem. Let me just remind you, going back a ways, we have talked about, let me go way back to, come on, here we go. We talked about the fundamental theorem of calculus. We motivated the fundamental theorem of calculus with the idea that change accumulates. And, a little algebraic, move there, and we end up with the fundamental theorem of calculus. Again, the fundamental idea, change accumulates. Associated idea of change density being the integrand, aka the derivative. But so anyway, the new point of view on derivatives is that it's if you were to think of change, the amount that a function changes between 2 points. If you were to think of that as a kind of a material, kind of a stuff, which it behaves as, look, we're computing it with an integral. It accumulates just like stuff. Let's view it as being a kind of a stuff. In that sense of viewing change as being stuff, that's what the derivative is. The derivative is change density. It's the density of that stuff called change. Anyway. Okay, then so we took those ideas and we say, hey, well, let's just apply them to a curve moving through space, and look, its change still accumulates. We write it down in a slightly different way, but look, my change in altitude along a road is likewise an accumulating thing, and details, and again, we end up with a theorem. This is the fundamental theorem of line integrals. So, same ideas, different context, different seeming theorem. Okay, and so we're going to keep going with it. I'm going to take these same exact ideas of, let me go back to where we are here now. Excuse me. One more. Here we are. Same ideas applied to a different context. The idea being that, look, there is something that's computed on the boundary, and up to now it's been change. But something that's computed on the boundary actually accumulates over the interior. That was our first observation about change. Right? And then I'm going to see if I can then rewrite that accumulation as an integral. Namely, I'd like to be able to take this, that thing, the thing that is accumulating, the little pieces of the accumulating quantity, and I would like to be able to come up with some sort of an associated notion of density. Namely, the accumulating quantity per unit size, I would like to be able to give that a name and a formula. Okay, so this is what I'm going to try to generalize now to a different setting. And it's going to be a really different setting. Instead of looking at an interval and saying, okay, but now imagine it being a curve. I mean, that's really not that big of a difference. An interval is a one-dimensional. You can imagine yourself moving along an interval. Well, you can imagine yourself moving along a curve, right? I mean, it's really kind of the same kind of a domain, just in a different context. We're now going to take these ideas and apply them to a very different context. And that is, we're not going to look at curves with boundaries that are points. We're going to look at solid two-dimensional regions. Sorry, it takes a long time to highlight. Okay, there's my solid two-dimensional region with boundary that consists of curves. And so if I were to talk about the boundary of that region, the boundary is it's a couple of curves. You know? Now, again, previously we were thinking of curves and boundary points. This is geometrically analogous, but really, really different because it's not a one-dimensional thing with zero-dimensional boundary. This is a two-dimensional thing that has a one-dimensional boundary, namely a curve. So that said, we're going to try to take these ideas here. I'm going to try to take this idea of that there's something computed on the boundary that is going to instead accumulate over the interior. I'm going to try to make sense out of that, but everything's going to have to change in order to do so. Okay. All right. So what are we computing on the boundary? Let's consider our options. Can I just do change again? Right? How much does some function change between the two boundary points? Right? You can't do that. There's infinitely many boundary points in this new context. I can't talk about f of b minus f of a. There's not just two boundary points. So we're going to toss that idea of change. That will not make any sense here at all. Right? Okay, so that's unfortunate. So there's lots of things that you could try. They will mostly fail. The analogy just won't be there. Stuff won't work. So I'm going to skip down to, let's not waste our time with a bunch of failures. Let me show you what is going to work. So I'm going to make a choice here. Again, the choice is going to seem arbitrary, but I emphasize this is the arbitrary choice that makes everything fit together. I'm choosing this so that stuff will work out. It is a choice. It is arbitrary, yes. But it's a really good one. All right? So here it is. The choice, the thing that we're going to compute on the boundary, is a vector line integral. So given a curve, and by the way, an oriented curve, and I'll come back and talk about orientation in a second, but given an oriented curve, I could instead of looking at a function and asking how much it changes, I'm going to look instead at a vector field and ask what is the vector line integral of that vector field along the curve. And it's going to turn out this is going to be a great choice, and everything's going to fall into place. We're going to get a result, and exactly why this is going to work is going to be a long discussion. It's going to take the rest of today's lecture and more. Okay. All right. Now, before I go on, I do want to go back. In order to do this, I do need for my curve here. Right, that curve's got to be oriented. When we do line integrals, we go along the curve in the direction that the curve is going. Right, and remember, it matters if you go along the curve one way versus if you go along the curve the other way. You don't get the same answer. You get exact negative if you go the wrong way on the curve. Right, so the direction matters. So which direction do we pick? Do we just always clockwise or always counterclockwise or something like that? And it turns out it's not quite that simple. Come back up here. Again, so we have this idea of our two-dimensional domain, which I won't fill in as thoroughly. We have the boundary well, let me say boundary curve, which I drew very quickly as that and this. What orientation do you pick? A lot of people do misstate this rule, by the way, so be careful. A lot of people say counterclockwise. And often that's correct. On the outer edge, yes, counterclockwise is the direction that you go. But that doesn't always hold. It's not always counterclockwise. For inside edges, you have to go clockwise. And if you say always counterclockwise, it will not work. The argument that we're about to do is going to crash and burn if you do it always counterclockwise. What you have to do is always go in the direction such that as you move in that direction, the domain is always on your left. That's the rule. And notice, if you're going around the outside part of the boundary, as you're going around the outside part of the boundary, the counterclockwise, right, the region will be on your left. Right? But if you're going around the inside part of the boundary, and my picture's getting to be a mess here, and let me zoom so we can see it more clearly. If you're going around the inside part of the boundary, you have to go clockwise in order to have the feature that as you move, the region is on your left. So that's the way geometry works. It's a little strange, but there is this kind of, a lot of people think of that geometry should always kind of work out in the expected kind of natural way, and there's a lot of consistency in geometry, and yeah, in some ways there is, and in some ways there isn't. Geometry's got a weird thing about it. This is not. This is unavoidably the way geometry is. It's weird. So be careful with that, and it takes a little bit of time to kind of wrap your brain around. On the left is not always counterclockwise. Okay. All right. Okay, so that said, there's our rule. That's the orientation that you take. Always go. I will admit that the word counterclockwise is fewer syllables than in the direction such that the solid whose boundary you're moving around is on your left. Right? So, I get it if you want to say counterclockwise very often. Just remember that it's a shorthand and it's not always correct. Okay, so let's ask now, what is this thing? This doesn't roll off the tongue as crisply as change, right? Oh, okay, my stylus is, there we go, okay. My computer went to sleep there for a moment. Okay, so here, this thing that we're trying to compute, this thing that I claim will be an accumulating quantity that's going to behave like change. What is this thing, right? How do I visualize this? What does this represent? It's not change, right? So what is it? And here's the word that we use to describe it. We call it circulation, and I think it's an extremely natural term. Call it. I argue as follows. Remember, we've already discussed that if you're thinking about fluids, right, an alternative point of view on a vector line integral is that you can think of it as, well, you're keeping track of how much the fluid is flowing along the curve as you move along the curve. And so in some sort of total sense that we don't have a previous word and concept for, right? In some sense, a vector line integral of a fluid is just keeping track of how much the fluid is flowing along the curve. Well, if you think about it, the curve here in this picture, the curve, by virtue of being a boundary, is making a full loop. Its tangent vector is going to go all the way around 360 degrees. Because it's a boundary, it's got to kind of loop back around on itself. So you might say the curve is making a circle-ish, something circle-like, in the sense that it comes back around on itself. And if you're keeping track of the extent to which the fluid is doing the same thing, then, again, here's kind of a picture of a fluid following somewhat along a curve, the fluid is going to kind of do the same thing too. The fluid is going to circulate, right? I mean, the fluid is, think about what this fluid is doing. That fluid is kind of doing the same thing, right? So the larger this integral is, to whatever extent I'll say that the fluid is in fact flowing along a curve that's going around in a loop, then the fluid is to that same extent, in some sense, going around a loop. And so thus the word circulation. Okay, very natural example. I don't know if y'all had the same experience that I did when you were growing up, but y'all know how air conditioners work, at home air conditioners. Not the physics of the the Carnot cycle and stuff, but there's a machine, right? And warm air goes in, cool air comes out, right? Well, that machine is not located inside of your living room, right? It's located outside or in your attic or something like that. So the way the air in your house gets cold is air goes into an air intake somewhere in your house, and then it goes off to where it gets made cold, and then it comes back, right? So that air intake is in some random hallway or something in your house, right? But then you want cold air coming out in, let's say, your bedroom. So the air intake is over here. Where the air is coming out is over there. So air comes out, and then it's going to have to make its way back over into the intake, and then go back through the cold air machine, and then go back out your vent in your bedroom, and then so the air in your house is circulating, right? And in order for that to happen, you have to keep the door. If there's a door here between the hall and your bedroom, if that door is closed, and the air can't get out, and therefore you can't push new air in if the air can't get out, and you'll stop the circulation. So I didn't really understand the geometry of all of this. I just thought the air conditioning was a magic thing. It just magic, presto, the air is cold, right? When I was a kid, and my dad was like, "Oh, you got to keep this door open for circulation." I'm like, "What are you talking about? The magic cold air machine just makes the air cold in the house." I didn't really understand that there was a flow of air, right? So anyway, that circulation, I've heard that word since I was about 5. I didn't know what it meant, right? But you can see here, this idea that the flow of this fluid, namely the air in our house, the term circulation is the perfect term to describe that. Okay, all right. So this is okay. Now I know this is a slow-moving conversation, right? So let me come back up here and remind you, we've got a new kind of a domain. We're looking at a two-dimensional domain. We've got a boundary curve with an associated notion of orientation. Also there. And so given a domain and its boundary, we have an object to compute. We have a quantity of interest that we hope is an accumulating quantity. And let me remind you of our goal. Our goal is to hope that this quantity of interest that we compute on the boundary, side note, we compute circulation on the boundary. Right? We would like to be able to conclude that, in fact, even though we computed on the boundary, that somehow, magically, it's actually accumulating as a summation over the interior. So that's not something that we're going to look at this picture and see. Right? So circulation, you see circulation happening around this curve. How would we see circulation as actually accumulating over this interior? It's really not obvious at all. But that's our goal. Fingers crossed. That's what we're hoping for. And now let me proceed along to show you why that's true. I'm going to start off with a simple example. Instead of chopping our domain up into lots of pieces, let me just chop it up into 2 pieces. So here's our domain. Remember, 2-dimensional domains now. Okay. Kind of like the curve when we were doing the fundamental theorem of line integrals. We had, domain, and we chopped the domain up into little sub-curves. Here we have a 2-dimensional region. We're going to chop it up into sub-regions. So my sub-regions are going to be this over here. Right? And then, oh gosh, I don't know if this is going to show up well, but this over here. Yeah? Okay. All right, so does boundary circulation accumulate? So what should it mean? Before we get into the equations, let's ask, what should it mean if boundary circulation were to accumulate? What would that look like? Well, okay, let's look at this piece over here on the left. What's the boundary circulation on that piece? Well, the boundary circulation on that piece is, we're going to look at line integral like this. Right? There's the boundary circulation on that piece. What about on this piece over here? What does boundary circulation look like on that piece? Well, boundary circulation would look like, again, follow the rules, counterclockwise, asterisk. That's what boundary circulation looks like on that piece. And the idea of accumulation is that what I associate to this piece of the domain, D1 on the left over there, what I associate to this piece of the domain, D2, on the right over there, I need for those quantities to add up to give me the same quantity associated to the whole. Well, the whole is this. What is the circulation around this piece? Well, the circulation around that piece is that. All right, so now this is what it would, and by the way, this is in the same sense that, what would it mean for mass to accumulate? Mass accumulating would mean I need the mass of this plus the mass of this to be the mass of the whole. Right? Well, I'm making the same question here. It's just now instead of mass of two-dimensional pieces, I'm talking about boundary circulation around two-dimensional pieces. Now, let me try to persuade you why this looks like it failed already. It looks like it failed already because going around this way and going around this way, there's all this junk in here in the middle that's part of both of those calculations, and that's not even present in what it needs to add up to, right? It needs to add up to this. So how could green plus blue add up to purple? Green and blue go into a bunch of territory where the purple curve doesn't even go over there. And this looks like a massive failure. The thing about it is, on that shared piece of boundary, on this piece of boundary, right, keeping in mind that we're going counterclockwise, here, let me switch to a pencil. Counterclockwise around that piece is that direction. Counterclockwise around that piece is that direction. And the awesome thing about how this works is that, that means that I am computing a couple of line integrals that are not part of what I need going all the way around, but they're exactly the same line integral twice, but with opposite directions, and therefore they're exact negatives of each other, and they cancel in a puff of smoke. And all that's left is exactly what we need. So boundary line integrals do accumulate. Let me draw the picture as a whole then. We've got that line integral in that direction and that line integral in that direction. We've got this line integral in that direction and that line integral in that direction. Does blue plus green add up to purple? Well, when you draw it like that, it doesn't look good. But when you realize that these two cancel, now it sure does. So boundary circulation accumulates. It's real weird. Oh, and it looks like I'm out of time. Okay, so this is a pretty good stopping point. We'll pick up here next time. See y'all later.